limits are probably the most important concept in this course, so we should really have a definition of what we mean by limit. So here is what we mean by limits. To say that the limit of f of x as x approaches a is equal to L means that f of x can be made as close to L as desired by making x close enough to a. There's a ton of subtlety to this definition, so it's worth looking at an example. So let's take a look at this function. This is the function that takes an input x and spits out x squared minus 1 divided by x minus 1. So let's try plugging the number 3 into this function. So I plug the number 3 into this function, and if I just compute, right, 3 squared minus 1 over 3 minus 1, well, that's 3 squared is 9, minus 1 is 8, 3 minus 1 is 2, and 8 over 2 is 4, and sure enough, out of this function comes the number 4. Let's look at that example again, but with a little bit more detail. This is actually a pretty complicated function, right? But I could open up the function, right, and take a look at how the function is actually doing its calculations. You could think of this function as having 3 different steps. Right? One of the steps squares its input and subtracts 1. So I calculate the numerator. Another step just subtracts 1 from its input. The outputs of those 2 steps then get plugged into the division, and that's how I get the output of this big complicated function. Now, something like x squared minus 1, you could also think of that as having some separate steps as well. But this is good for right now. Okay, now let's see what happens. I take the number 3 and I plug it into the function. Right? Now I'm going to be calculating the numerator and denominator separately. So I'll take those 3's, and up here I'll look at 3 squared minus 1, and I'll get out 8. And down here, 3 minus 1 became 2. Now the 8 and the 2 get plugged into the division, and 8 over 2 is 4. And that becomes the output of the function. Right? Inputs 3, outputs 4. But when I look at it this way, I can see how all the steps are playing out. Okay, I evaluate the function at 3, but who cares? Well, let's try to evaluate the function at 1 instead of at 3. So what happens when we plug in the number 1 into this function? I've got the number 1 here. I want to look inside again. I'm going to open up this function. Now imagine I got this number 1. I'm going to plug it into the function. Right? Now I'm going to be evaluating the numerator and denominator separately, so I'm going to take this 1 and split it up and plug it in the numerator and denominator. The numerator sends its input to its input squared minus 1. So 1 squared minus 1 is 0, and the same thing down here. 1 minus 1 is 0. Now I've got 0 and 0, which I'm going to be plugging into the division. Whoa, okay. Very bad, right? I'm dividing by 0, and I cannot proceed. So this function is not defined at 1. So I can't plug 1 into the function, but if I wanted to figure out what the function's value was that inputs near 1, I could do that. So let's try to plug in 1.1 instead. So let's plug 1.1 into this function. I can't plug in 1 because I'd be dividing by 0, but let's try plugging in 1.1. I'm going to open up the function again. I'm going to take 1.1, plug it into the function. Now, 1.1 is going to be evaluated in the numerator and the denominator. 1.1 squared minus 1 is 0.21, and 1.1 minus 1 became 0.1. Now 0.21 and 0.1 are going into the division, and 0.21 divided by 0.1 is 2.1. So when I evaluate the function at 1.1, I get out 2.1. Instead of just plugging in one value, let's plug in a whole bunch of values. We'll make a table. So here's that same function again. F of x is x squared minus 1 over x minus 1. Now I can't plug 1 into the function, because if I plug in 1, I'd be dividing by 0, and I can't divide by 0. 1 isn't in the domain of this function. But I can plug in numbers near 1. Right? And we saw that 1.1, if I plug in that, I get 2.1. Right? And if I plug in 1.01, I get 2.01. If I plug in 1.001, I get 2.001, right? And so on. If I plug in 1.0000001, I get out 2.001. Right? Well, what's going on here? I could summarize this situation by saying the following. the limit of x squared minus 1 over x minus 1 as x approaches 1 is equal to 2. Why is that? Well, this is because I can make x squared minus 1 over x minus 1 as close to 2 as I want if I make x close enough to 1. Let's see. Here's my table. All right. If you want the output of this function to be within a billionth of 2, all you need to do is to make sure that your input is within a trillionth of 1. Right? As long as your input is close enough to 1, you can guarantee that your output is as close to 2 as you like. This is just looking at a table of values, maybe a dozen values and seeing what they're getting close to. It'd be a lot better if there were a more convincing argument. So let's go back to our definition of limit. To say the limit of f of x equals L means that f of x can be made as close to L as you desire by making x close enough to A. And let me emphasize something. Close enough, but not equal to A. Why does something like this matter? Well, let's go back to our example. In our example, the function wasn't defined at 1. But the limit doesn't depend upon the function's value at 1. It only depends upon the function's value near 1. So x squared minus 1 over x minus 1 is equal to x plus 1 as long as x isn't equal to 1. Right? As long as x isn't 1, this is a true statement. So now what's the limit as x goes to 1 of x squared minus 1 over x minus 1? Well, this is the limit as x approaches 1 of x plus 1. Because the limit doesn't depend upon the value of the function at 1. It only depends upon the values of the function near 1. And as a result, these two things have the same limit. Even better, the limit of x plus 1 as x approaches 1, well, that's the limit of a sum. And the limit of a sum is the sum of the limits. So I can rewrite this limit as the limit as x goes to 1 of x plus the limit as x goes to 1 of 1. Now what's the limit of x as x goes to 1? Well, that's asking what can I make x close to if I make x close enough to 1? Well, that's 1. And the limit of 1 as x goes to 1 is asking me what's 1 close to when x is close. Well, there's not even an x in this, right? Wiggling x doesn't affect this at all. So that limit's also 1. And 1 plus 1 is 2. So indeed, the limit of x squared minus 1 over x minus 1 as x approaches 1 is 2. Limits provide information about what a function's values are approaching. Right? It's a way of accessing otherwise forbidden information. I might not be able to plug in the value 1 because that would have entailed dividing by 0. And yet I know that the function's output is as close to 2 as I like, as long as the input is close to but not equal to 1.